Okay, number 13, we want to use the limit process to find the area. Now, the limit, we're going to be talking about the limit as n approaches infinity. The limit's at infinity. To find the area of the region between the graph of the function and the x-axis over the given interval. Okay, so we're going to be thinking about the x-axis. We're thinking about being within the interval of 1 to 3. We're not going to graph this exactly here. We're just going to try to understand that that is a parabola. A is negative, so it's a parabola that opens down. So I'm just going to draw a general curve, not knowing exactly where it is, but we're just wanting to get a visual aid. And so we have some type of parabola opening down. We want to find the area of the region bounded between that curve and the positive x-axis. And so we're talking about the area underneath that, the area within that blue region there, okay? Now, when we think about that, what we did earlier in calculus at the very first of the year is we said, well, if we would subdivide this into rectangles, then we would be able to add those rectangles areas, and that would estimate the area under that curve. Now, we know that the height or the length, the width, the height of this particular rectangle could be found by finding the function value at the right edge of that rectangle. And to find the height, the length of this rectangle, or the height of it, we could find the function value at the right side of that rectangle. Okay? And so we found the area of each rectangle and added them up. All right. Now, when we think about the width of a rectangle, when we think about the width of a rectangle, we're actually thinking about the spacing between the rectangles. My mouse died on me there. The spacing between the rectangles, in other words, the space here is 1, you see. And then the length is actually the function value, right? The function value at the right bound of the rectangle. All right. Now, we talked about that, and then we said, okay, if we would create more and more rectangles, then we would get closer and closer to the actual area under the curve. And then when we did that, we said, okay, now we've got these 4 rectangles. Let's just look at that. We can find the width of a rectangle by saying, okay, the whole distance is 3 minus 1, the upper bound minus the lower bound. And then if we divide that by the number of rectangles, 1, 2, 3, 4, we would have 2 over 4, which is 0.5, which actually gives me my width, or my spacing. Each of these would be 0.5. If I'm running from 1 to 3 and I have 4 rectangles in there. So you can see that we can find the spacing or the width by taking the upper bound minus the lower bound divided by the number of rectangles. Now, if we're saying we want our number of rectangles to reach infinity, then we would have a situation where we're creating a limit as n approaches infinity, n representing the number of rectangles that we're placing under that curve. So upper bound minus lower bound divided by the number of rectangles would give us the width or the spacing, okay? Now, we'll just continue with that idea. If we continue with that idea, then what we would have is the upper bound 3 minus the lower bound 1 divided by the number of rectangles n would give us 2 over n as a variable expression for the width of an infinite number of rectangles under that curve. Now, if I wanted the length of this particular rectangle, then I would have to think about having where I started plus my gap, right? This right corner is at the start 1 plus the gap 0.5. Start plus gap. And if I wanted the function value of the second one, it would be the start 1 plus the gap 0.5 plus another gap of 0.5. And if I wanted the right side of this rectangle, it would be the start 1 plus the gap 0.5 plus the gap 0.5 plus the gap 0.5. And to find this one, we would just add that gap again. So we can use a counting mechanism to add the gap. We can use a counting mechanism to add the gap. Now, we know that the area of a rectangle is length times width. We know that we can write width in terms of spacing in relationship to the number of triangles n, and we can write the length in terms of the function value at that point. All right. Now, if I wanted the width of that first rectangle, the length of that first rectangle, that function value, then I would say, well, I want f of where I started 1 plus the gap, which is represented as a variable as 2 over n, but so that I get the width of the first rectangle, second rectangle, third rectangle, I'm going to put in my counting mechanism of I. Now, I want to take a moment to explain what we're doing with that I. If we were actually going to find the areas of all of that, we could find the area of each rectangle. And looking at my 4 rectangles that I have, the area of the first rectangle would be the function value at 1, my start, plus one of those gaps of 0.5, which we know would put us at 1.5, times the width of the rectangle 0.5. That would give me the area of the first rectangle. The area of the second rectangle would be the function value at 1 plus 2 gaps times the width of 0.5. And we could continue that on. So as we see that we could factor out the 0.5, and then we could have 0.5 times the sum of these widths. Well, we can write that as a summation. Okay? And my counting mechanism is attached to the width. I need that width once, I need that width twice, I need the width 3 times. And so that's going to give us, as we apply the counting mechanism, each of those heights or each of those lengths of the rectangle. And so we're going to have the width times the summation of the lengths. Okay, so let's apply that then to limit as x approaches infinity and the summation. Okay, so what we're going to have is the limit as n approaches infinity of the summation of all of those rectangles. Now, my counting mechanism is I, and it's going to run from 1, I'm going to add that gap once, into the number of rectangles times, and the number of rectangles is going to be infinity, okay? Of my formula, which is the length of each rectangle, which is that 1 plus 2I over n, times the width of each rectangle, which was that 2 over n. So we have created a summation formula that will give us length times width of every rectangle into infinity, and we can find the exact value under that curve. Okay? We see we got our equation. All right. Now what we need to do is just simply solve that equation. We need to simply solve that equation. Okay? So how could we do that? Well, let's rewrite the first part. The limit as n approaches infinity of the summation as I runs from 1 to n of the function value of that. Now, here's my function, right? There's the next square there. So I'm going to have 16 minus, in place of x, I'm going to put 1 plus 2I over n squared. See that? I replace my x with 1 plus 2I over n. I'm going to remove this now. And then I better put this in a bracket. Chopped off my 16. Times, that's my length, right? The summations of my length times my width of 2 over n. Okay? Notice that my counting mechanism is still in there. Okay? So we have the function value at the right edge of each of those rectangles times the width of each of those rectangles. Okay? Now, we need to solve this, and remember when we're doing summation, we need to get it in terms of I and I squared. Okay? We need to get it in terms of I and I squared. Now, what's one thing that we could go ahead and do if we wanted to do? We could pull out that to the end, right? Anytime we want to pull that out, because a summation times a constant is the constant times the summation. So at any time we want, we can go ahead and pull that out. So we could think of this as the limit as n approaches infinity of 2 over n times the summation as I runs from 1 to n of 16 minus 1 plus 2 over n squared. To I, thank you, over n squared, 2I over n quantity squared. Okay, so we got to there. All right, I'm going to have to remove stuff as we go because of space here. So I'm going to remove that. Now, we need to expand this, okay? We need to expand that. So we're going to think of it as 1 plus 2 over n times itself 1 plus 2 over n, right? Which is going to give us 1 plus 2 of those, 2 over n's, right? Which would be 4 over n. I left out the I again. Thank you. So we have 2 of those, 2i over n's, which would be 4i over n. Thank you. Plus 2i over n times itself, which would be 4i squared over n squared. We've got to be very careful. I'm leaving off i's and all kinds of things. Okay? You see how we got that? And then we had a minus in front of that. See that? And I'm going to distribute that minus, which would make it a minus 1, minus 4i over n, minus 4i squared over n squared. And then I've got a 16, right? I'm going to simplify everything in that parenthesis here for just a second, and then we'll just magically stick it in. Okay, I didn't want this to just appear. Okay, you can do the math. I want to do it for. So we're going to have 16 minus 1 is 15, right? So we're going to have 15 minus 4i over n minus 4i squared over n squared. Now, that's what all of that turns into, right? Okay. So we have the limit as n approaches infinity of the summation as I runs from 1 to n of 15 minus 4i over n minus 4i squared over n squared.
You gotta put your width on your 2n.
Yeah, I meant to put that in there. Thank you. The limit as n approaches infinity, we had factored out that width of 2 over n times, and then that summation turned into 15 minus 4i over n minus 4i squared over n. It's getting a little nicer because it appears now that what we have is something in terms of I and I squared. Okay? So we're getting closer to a format that we understand. Okay? Any questions on that? Okay, I'm going to remove the work at the top so I'll have another place to write. Okay, so remember that the summation of a sum or difference is the sum or difference of the summations, right? So we could think of this as the limit as n approaches infinity of 2 over n times the summation as I runs from 1 to n of 15 minus, now remember we can factor out, we want to isolate that I, right? So we're going to have minus 4 over n of the summation as I runs from 1 to n of I of I. I need to remove some more things here. And then we have on the next portion of minus 4 over n squared that we want to pull off so we can isolate the I squared. So we're going to have minus 4 over n squared of the summation as I runs from 1 to n of I squared. Okay, so that's where we're at. Okay, now, we need to remember some stuff now. The limit as n approaches infinity, the limit as n approaches infinity of 2 over n times. Now, how do you expand that? The summation of a constant. Remember what it's going to be? Constant times upper bound. Do you remember that? The summation of a constant is constant times upper bound. Okay, you need to remember that rule. All right? Minus 4 over n times. What about I? I is n times n minus 1 over 2. Remember that? Plus 1. N times n plus 1 over 2. And cubed. I don't know why that happened. Minus 4 over n squared. And then the summation of I, so we would have times. The summation of I squared, is n times n plus 1 times 2n plus 1 over 6. And we would need to close that. And then we would need to close our bracket. Okay? Let's see how we got to there. Okay, so we need to simplify all of this stuff. So it'd be probably better to go ahead and do that, maybe, and then do all of this. So let's just kind of take care of all of that in here first. So we're going to kind of come over here to the side. That would be n squared plus n over 2, right? I'm going to do this whole thing. And then times negative 4 over n, which would give me negative 4n squared over 2n minus 4n over 2n. Are you seeing that? Which gives me negative 2n minus 2. So this turns into minus 2n minus 2. And then if we do this part, if I do the n plus 1 times 2n plus 1, I'm going to have 2n squared plus 3n plus 1. And then times that n gives me 2n cubed plus 3n squared plus n. And then I'm going to divide by 6, and I'm going to have a 6 under each one of those. See what I did? And then I'm going to have a negative 4 over n squared times each of those. So I'm going to have a negative 8 over 6, which is a negative 4 over 3. I've got an n cubed on top and an n squared on bottom, so I've got an n there. And then I've got a negative 4 times 3 is a negative 12 divided by 6 is a negative 2. And my n's would go out, so I have a minus 2 there. And then I have a negative 4 and a 6, which is a negative 2 and a 3, negative 2 over 3. And I've got an n squared on bottom and an n on top, so I'm going to have an n on bottom. Let me check for mistakes to make sure there's no errors there. Okay, so this turns into, this part turns into a minus 4 over 3 n minus 2 and a minus 2 over 3n. And I still have my 15 in here. I'm just going to put a bracket. And I still have my 2 over n, and I still have limit as n approaches infinity. So now I have a limit as n approaches infinity of 2 over n times that. Okay? Okay, so now we want to distribute that 2 over n. So we're going to have the limit as n approaches infinity of, we've got 2n over n times 15 over n, which makes a 30. And then we have the 2 over n minus the 2n. That would give us a minus 4, and the n's would go out, so minus 4. We would have a negative 4 over n after that. We would have an 8 over 3, and the n's go out, so a minus 8 over 3 after that. We would have a minus 4 over n after that. We would have a minus 4 over 3n squared after that. So we got that. Okay. Now, when we're talking about the limit as n approaches infinity, everything with a variable in the denominator turns to a 0, right? So those all go to 0. So now we're left with 30 minus 4 minus 8 over 3. 30 minus 4 minus 8 over 3. And when you calculate that, you get negative 23 1/3. Negative 23, or excuse me, 23. So I was looking at a negative sign, it stayed in my head. Positive 23 1/3. For the area of that curve, and that's the exact area. Pretty amazing what calculus has brought us to. Remember, at the first of the year, we were estimating by creating more and more rectangles, and now we're able to say, let's let the number of rectangles be infinity, and let's come up with the exact area under the curve. Any questions on number 13? All right, appreciate you.